Organizers for inviting me here. I'm from Georgetown University, and I'm going to tell you about work that was funded from the NSF. We're taught now that one of the important things when you're teaching classes is not to ignore current events and even to bring them into the classroom. So I'm going to bring them into our talk. I would actually like to start with a moment of silence to honor the citizens of Ukraine and the families of Uvalde, Texas, given the amazing tragedies that we've been experiencing. So thank you for that. Quantum information science has three pillars to it. The first one is quantum computing, and here I've selected an image of the IBM quantum computer, and I've shown an algorithm for the phase estimation. I've shown a diagram of the phase estimation algorithm on the right. Quantum communication is the second pillar, and here I'm showing a quantum key distribution system and the famous BB84 communication protocol. And then the third is quantum sensing, and here I'm showing a global positioning satellite and the laser interferometry gravitational wave observatory, which is probably the most sensitive instrument that has ever been built by humankind. And there's a lot of interest in making sure that we physicists are teaching quantum information science in some fashion to help prepare people for the future. And physicists actually have the strongest overlap with the quantum sensing pillar. And I want to talk to you about how to supercharge quantum mechanics courses to really provide a strong foundation for quantum sensing. This is just showing you that sensing is a big industry already. The GPS is a huge industry. It is in the $120 billion projected for 2025. Other quantum sensing is growing. It's nowhere near as large of an industry. Here they're talking about things like $3 billion in 2028. The US government has given out an imperative that we need to create quantum-enabled workforce. And here they're talking about making sure that we have enough people for careers that can develop quantum technologies, and they've created a pyramid which starts at the bottom with people who essentially know nothing about quantum mechanics, and then you have people who are quantum mechanically aware, people who are quantum mechanically proficient, and people who are experts. And when we're talking about teaching undergraduates, we're really focusing on the quantum mechanics aware and quantum mechanics proficient populations in this pyramid. So, surprisingly, there's not a lot of physics education research that tells us what doesn't work, but I think anyone who is taught quantum mechanics empirically knows that teaching quantum mechanics using standard differential equations doesn't work very well with the students. At the very least, we recognize that we teach it 3 times almost the identical way every time. Sophomore, upper level, undergraduate, and graduate teaching almost the exact same material, almost the exact same way. And often, even after seeing it 3 times, students struggle with it. The history of where this comes from is from Oppenheimer, who gave a very famous set of lectures at University of California at the end of World War II. And then this was written in a book by Schiff. And at about the same time, Dirac's 3rd edition came out. That was in 1947. Schiff was in 1949. And pretty much all of our quantum pedagogy is based on this error. This is almost 70 years old, and we haven't really changed it. So your first question would be, okay, maybe differential equation doesn't work. What am I going to do? How can I teach it otherwise? Well, the first thing we should do, and this is something that physics education research really tries to emphasize, is we should focus on conceptual ideas. And for quantum mechanics, I've listed 5 conceptual ideas here: superposition, entanglement, complementarity, tagging, and measurement. The 4th one, tagging, you might not be so familiar with. That is a situation where you're creating entangled states in a reversible way, and those are the kinds of things that are used in delayed choice experiments, or can be used in delayed choice experiments. And there are a lot of resources for these conceptual ideas. Feynman wrote a wonderful book called QED, where he teaches about the theory of light using a very simple model that actually incorporates all of the quantum mechanical ideas completely correctly. Daniel Steyer has a wonderful book called The Strange World of Quantum Mechanics, which does the same thing, but for Stern-Gerlach experiments. And then Ed Taylor came up with the idea that these textbooks will be much better if you could actually animate the figures that are in the textbooks. And I'm going to show you the kind of animation that I use. This is doing a Stern-Gerlach experiment. We start off by teaching students about a classical Stern-Gerlach experiment, which is a current loop indicated by that arrow that's moving around in a circle, and it has an effective magnetic needle, which is the arrow that points up. And as it goes through this inhomogeneous magnet, it precesses, which you can clearly see. And then it also feels a force on it depending upon what the projection of that effective needle is on the axis of the magnetic field. And that push will push the atom into a particular location. And in the classical situation, you get all possible values between some maximum and minimum. When we go to looking at what happens with the quantum case, we don't know exactly what it is. So we illustrate it as just a vanilla sphere. But now when we put it through this device, we find it's not going everywhere possible between a maximum and a minimum. It's just picking two values. And we're just getting two results. And if we change the orientation of the magnet, we find that we still get the same result. We get just two different values. And this is sort of at the heart of what is the difference between a quantum mechanical Stern-Gerlach experiment and a classical experiment. And we kind of bring it to life by showing these types of animations. These are JavaScript animations that you can just, everyone can run them easily just through a web browser. The second thing is to use algebraic operator methods to develop the material. There are a number of benefits to this, but many people aren't familiar with it. It essentially extends the operator solution of the simple harmonic oscillator, which whenever you teach it, the students really like doing it with the operators as opposed to doing it with differential equations. I don't think I've met a student yet who says, no, give me the differential equations. I really love doing that stuff. This method can be extended to every exactly solvable problem that we teach in quantum mechanics. And Schrödinger worked this out in the early 1940s. You can actually get wave functions completely algebraically as well. So you don't need differential equations to get the wave functions either. This is more recent work that I've been involved in. The third thing is we want to make sure we emphasize experiments, not the mathematics. After all, we are physicists. We're teaching we would like to teach them about experimental ideas and how experiments work, and we're not mathematicians trying to just teach them, here's how you solve differential equations using power series methods. So I teach a one-semester-long class in quantum mechanics, and this is a word cloud of all of the different experiments that I cover. And there's a lot of interesting things that aren't in many textbooks. Like I cover Hong-Ou-Mandel experiment, I cover delayed choice experiments, Hanbury-Brown and Twist, the proton charge radius, the discovery of the deuteron, E2E spectroscopy, which is the way that you can actually image the hydrogen atom wave function, time of flight, which I'll have some more to talk about, Bell experiments, Pickering-Fowler lines, which is a very interesting experiment in the history of quantum mechanics, and many others. So I want to give you an idea of how working with operators can avoid you from having to postulate things simply because you don't have any other way of explaining them. And I'm going to start by talking about the canonical commutation relation and how you can relate that to experiment. The starting point is the postulate that quantum mechanics must be described through examining matrix elements of operators, and their time dependence is given by the difference of the energies of the states that are in the matrix element. This is what Heisenberg proposed in 1925, which started the modern era of quantum mechanics. So the way that we motivate it, we have 5 ideas. The first is that atoms have sharp spectral lines. And this is a nice thing that you can demonstrate with the students by using little pocket spectrometers and having them look at fluorescent lights if you have them in the classroom. We use the Planck-Einstein relation that relates the frequency of light to the energy. We use the Bohr idea that transitions only occur between stationary states. And then this is the Einstein idea that, the Heisenberg idea that the matrix elements oscillate harmonically at the frequency given by their energy difference. And then finally, we just simply use the fact that the total energy is the kinetic energy plus the potential energy. So here's how it works, and this is an idea that came from Herbert Green. It's in his textbook. He wrote a wonderful textbook in the 1960s. You start with a hypervirial theorem. Of course, you don't tell the students you're working with a hypervirial theorem. That'll get them to stop listening to anything that you have to say. But you simply say, look, let's investigate this matrix element of the position operator with a commutator with the Hamiltonian between another state. And because they're eigenstates of the Hamiltonian, you can evaluate this immediately as the energy difference times the expectation value of position. And then using Planck-Einstein, this becomes minus h bar times that frequency difference, omega mn, between the two. Now use the fact that a harmonically varying function, because this is the hypothesis that Heisenberg told us, this matrix element is harmonically varying in time, its time derivative is proportional to the frequency. And so I can rewrite this as a time derivative. And because I'm working in the Heisenberg representation, that time derivative is going to go into the operator. So I'm now looking at an expectation value of dq dt. Well, now that's just the velocity, which I can write as the momentum divided by the mass. Okay? Now, that completes the first step of this derivation. The second step, we just evaluate the commutator. I have the commutator of q with p squared over 2m and q with v of q. It obviously commutes with v of q because q commutes with itself. For the commutator with the momentum, we just use the Leibniz rule to expand this into the two pieces. And now, when we plug that into the matrix element, if we make the assumption, and this is where it's not a full derivation, if we make the assumption that this commutator is a number, I can pull it out. And now you see this coefficient has to equal this coefficient because it's the same thing, the same operator, same expectation value. So you immediately get that if the commutator of q with p is a number, it must be IH bar. So you don't have to postulate it. You don't have to bring in Poisson brackets or any of the other things that are typically done. It just follows directly from the fact that atomic spectra have sharp lines. So it's experimentally motivated. It doesn't need to be a postulate, and it for sure doesn't need you to talk about Poisson brackets, which most undergraduates haven't seen and don't understand, or any of the other motivations that you find in most textbooks. Okay. Asher Perez wrote a very interesting textbook, and I love this quote from him. He starts, it's like chapter 9 or something in his book on measurement. He says, quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. So we want to be sure that we teach quantum science and not quantum science fiction. And I'll just say it's generically a bad idea to have a mathematician define for you what the theory of measurement is in quantum mechanics, but that's what we're doing here with John von Neumann. What he says is to measure a quantum observable, what we do is we prepare the state that we want to measure. That sounds fine. We entangle the state uniquely with some apparatus so that the pointer states of the apparatus are correlated with the eigenstates of the measured operator. And then we have this measurement problem thing. There's a collapse of the wave function, or if you want, you can use decoherence to fix the pointer position because your apparatus is macroscopic compared to the system that you're measuring. And that's our theory of measurement. This is that's what we all taught. But I'm not really sure I know a single quantum experiment that actually operates this way. And in fact, Schrödinger, after von Neumann introduced this theory in the 1950s, he said, you know, it's a beautiful theory that you've developed, but I don't think it applies to any experiment. And let me show you what I mean by that. And so the question is, why do we teach a measurement theory that possibly has no basis in reality? So Paul Dirac has a nice quote, the only object of theoretical physics is to calculate results that can be compared to experiment. I think we should keep that in mind. And we should really understand what the experiments are and how they work. So how do we actually measure quantum objects? In many cases, we infer the properties from a very clever experimental design. Oftentimes, the measurements are destructive. Think about photon detectors. The photon gets destroyed and creates in a photodiode, it creates an avalanche of electrons that create enough signal that you can measure the signal. In a situation like that, you know exactly when the experiment occurs. There's no measurement problem. You destroyed the particle at the time of the measurement in the device. Having single quanta sensitivity and manipulating the single quanta, that's the aspects of measurement that we really want to teach students and we want to get them to learn. So I'm going to just show you a familiar example to people in this audience, a single photon source in detection. Oftentimes textbooks say, oh, just take a laser and dim it so that you only get one photon going through over the time of the experiment. That is not a single photon source, because lasers always are created from coherent states of light, and there's photon bunching, and even though that argument sounds very sound, you often will have multiple photons in your device at any given time. But this is the first single photon source, the calcium atom cascade source, and here the way that it works is that you have two lasers that excite to an upper state. You have a fairly quick decay to an intermediate state, and then a decay back to the ground state. So once you see this photon, which is a different color than this one, once you see this photon, you know within a nanosecond that second photon is going to come out. And these experiments, you know, so you typically have your calcium here. Here you detect the heralding photon, and then the other one is coming out in the opposite direction. You put it through your device, and you detect the signal. And lo and behold, it fits what you would expect it to fit. You get no photons until the photon has had enough time to travel down this waveguide to actually get to your detector. That's what's happening here. And then because it is a random process, that is an exponential decay of that intermediate state, you get an exponential decay of the photon signal after that point in time, and that correlates with the lifetime of that intermediate state. Single photons are characterized by the fact that they can only be detected once, and we measure this using this famous G2, here it's called alpha C, where you just take your photon source, put it on a beam splitter, you have two detectors, and you ask how often do the two detectors fire at the same time? If I have single photon sources, they should never fire at the same time. So if you look at the number of correlated electrons divided by the number that go into the up detector, the number that go into the right detector, and indeed taking this ratio, what you find is when that ratio is less than 1, then you have a single photon source. And this is real data that was taken a number of years ago, and they were getting down to this G2 measurement being on the order of 0.1 or so. I'm sure that one can do much better than that now. But I'm not a quantum optics experimentalist, so I don't know the current records on what that is. Let me ask you another question. How do you respond to this question? This appeared on Quora. What variables can be measured in physics? Is it only the position of a particle that is always measured and the rest of the variables inferred from it? So an answer that came up was dynamic variables include position, momentum, phase, spin orientation, and polarization can be measured independently, but non-commuting operators cannot be measured at the same time. And many of you might be sitting there in the audience nodding your head, and I call that if it is a Hermitian operator, it can be measured, but it must respect uncertainty. Of course, but isn't your detector located somewhere? Isn't it always de facto measuring the position of whatever it's actually detecting, along with whatever else it might be measuring? Let's unpack this a little bit further. How do you actually measure momentum? I know of one quantum textbook out of all of the hundreds that are out there that actually tries to answer this question instead of just saying, it's a Hermitian operator, you can measure it. Many textbooks say that you can measure it, they just don't tell you how. If you were in the previous session, you saw a way to do it, time of flight. So let's unpack this. An event starts a clock, the particle travels through free space to the detector where it's detected. We divide the distance traveled by the time to compute the speed. From the speed, we get the momentum. All sounds great. At the instant of measurement, we know the position and the momentum of the particle at the same moment. Is that a problem? Here's a nice recent experiment from Cindy Riegel's group that used time of flight to measure the momentum distribution of the harmonic oscillator in the ground state and the first two excited states, which are the images shown on the right. Those are actual images of a probability distribution of an atom in a harmonic potential. It's beautiful stuff. This is what we should be showing students in experiments. And of course, it's not a problem that you can measure both at the same time. Uncertainty comes from looking at repeating the measurement and then getting the distribution. And in this case, it's the uncertainty of the initial setup that's giving this momentum distribution, because when I take a system in a wave packet and I let it expand freely, the momentum distribution doesn't change. The position distribution gets extended. It gets magnified, and that's what I can measure. So you can think of these measurements both as a momentum distribution or as a position measurement that has been magnified, but the shape has not changed. So it's simply not true to say that you cannot measure position and momentum at the same time, and I would encourage you not to say this to your students. You can, however, tell them that you can't create a quantum state that has a well-defined position and momentum at the same time. That for sure is true. Quantum measurement is difficult and subtle, and we should always describe precisely how it can be done and never just say it can be done. We should never talk about an experiment without describing how the experiment is performed. I'm going to now show you a video. I hope I'm not going to run out of time. This is a beautiful delayed choice experiment. Everyone should show these kinds of videos. This is from Paul Nord from Valparaiso, who does masterful demonstrations. He has a whole YouTube channel. I encourage you to look at it. Here we're looking at diffraction of a single wire, and you get this beautiful diffraction pattern when you put the laser across the single wire. Now what he's going to do is has the exact same kind of source, but he's put polarizers, one vertical and one horizontal, on two sides. And you can see he's moving that polarizer around. You can see different polarizations on the two sides. So now when the light goes through, you have which-way information. So this is a great way of talking about complementarity. And indeed, now when you look at it, there's no diffraction pattern, as you're going to see. You can take a polarizer, put it in front, and get all of the light from either side, the left side or the right side, depending on how you put the polarizer. That's what he's going to do next. So that's the light from both sides. Now he's going to rotate the polarizer. That's the light from just one side. I think he might be rotating at 90 degrees and showing the light from the other side, or maybe he just removed the polarizer at that stage. And now what he's going to do is rotate it by 45 degrees. Here's a delayed choice experiment. And boom, there you get the interference comes back. So these are beautiful things that we should be teaching our students in quantum mechanics classes. Okay. The last thing I'm going to talk about, interaction-free experiments. This is another wonderful thing that has been developed, modern topics that often don't get into textbooks. And yet one of the oldest experiments is a beautiful interaction-free experiment. It's in every quantum textbook, but no one ever says it's an interaction-free experiment. I'll let you think about it for about 2 seconds to see if you can come up with a guess for yourself as to what it is. And it's, of course, the Millikan oil drop experiment, but of course, the person who actually did the experiment was his student Fletcher. And if you think about it, what are we doing? We put a charge on an oil drop, we measure it, we apply a voltage, and we measure a time for it to move. There's no wave function collapse. There's no entangling with some device and hoping that decoherence scatters. No, we're counting electrons by measuring, applying a voltage and measuring a time. It's very similar to time of flight experiment. So what I would like to do is encourage you to teach about real experiments when we teach quantum mechanics. And I think we have a great opportunity here to actually improve quantum mechanics instruction, which has stagnated for 7 decades. And I would encourage you to join with those of us who are trying to do that. And then I will end by thanking the National Science Foundation, who funded some of this work. At Georgetown, we have a Center for New Designs in Learning and Scholarship. All of these courses that I have, you can look at on edX, and I get some money from these 2 lovely people from Georgetown University. If you want to get information about all of the educational projects I work on, this site, quantum.georgetown.domains, will hold all of that. I have a course, the undergraduate course on quantum mechanics is at this link. And then I also have a shortened course of that, which focuses just on the conceptual ideas that I call Quantum Mechanics for Everyone. That's also on edX. And the latter courses had about 50,000 students go through it. The undergraduate courses had about 2,000 to 3,000 students. I say go through. They've enrolled. The total number that have graduated is always much less in MOOCs than that. But at least that's the number of students who've at least looked at something in the class. And with that, I want to thank you.
From William and Mary. I'm about to teach the quantum mechanics for the first time, so I'm very excited about this. I thought a lot about very practical questions. What is the best or textbook which you would recommend for this, for the...
So if you want to teach it this way, there is no great textbook because no one has written a textbook. So if you want to look at ways to teach this operator method, Green's textbook and Ohanian's textbook are two textbooks that cover it in fairly extensive detail. You know, bringing in experiments and things, you're going to probably want to consult things like American Journal of Physics and other things like that, where people have talked about these different kinds of ideas for how to do it. And if you go to that top resource, you can see I have a lot of materials there. All of the animations and things that I use, they're freely available from GitHub. You can just take them and use them however you would like. And I will just plug that I'm working on a book that's going to be called Quantum Mechanics Without Calculus, but it'll be a few more years before it's out.
So I really appreciate the idea of thinking about experiments within sort of traditional lecture courses. What role do you feel for actually having students work with the experiments and how we, unfortunately, unnaturally divide labs and theory? Do you have any ideas about how to combine those?
Oh, I think it would be wonderful if we actually had a lab component for a quantum mechanics class and we brought in a number of these quantum optics experiments can be done. You saw that delayed choice is a very simple demonstration. So yeah, I think a lot of these can actually be done, and I think it would be wonderful if we could actually try to incorporate that more in the undergraduate classes as well. Yeah. For sure, if you're going to teach quantum sensing, it doesn't make any sense to have a purely theoretical course. You want to actually have students doing some quantum sensing during the course itself. We just haven't structured them that way. That change is probably very difficult to do unless you're in a small department.
Oh, I just wanted to ask you if for that proof for the commutation relationship, do your students already know how to handle the commutator, those kind of things? Because usually they struggle, like that's a very beautiful proof if you already know how to do all that algebra.
Yeah, so if you focus on conceptual ideas first, the first 4 weeks of my course are purely conceptual ideas, and I develop the Dirac formalism with that. Then the first system I look at is spin, and we develop the spin operators, spin algebra, Pauli matrices, Pauli identity, spin matrix identities, and so forth. And by the time I get to that commutator part, they've already seen operators quite a bit. They've seen states, and so it's a fairly natural thing to do. It's much more difficult if you want to just start with wave functions in position space and throw that proof at them. It might be too much for them.
Related question. So it's a question of students visualizing with, or thinking algebraically versus thinking geometrically. Most of my students seem to prefer and be able to think geometrically better with pictures, graphs, etc. But I'd really like to be able to hit them with the algebraic approaches because I think that's really beautiful. Suggestions for getting students to...
Because it's not that difficult to get wave functions as well as... So when you work algebraically, the interesting thing that many of us don't know, although you can recognize it both in harmonic oscillator and in angular momentum, which are problems that are in most textbooks, is you get the states and the eigenvalues without the wave functions. That's the beauty of the algebraic method, is you don't actually need to have the wave function to get the energies. But because you can get the wave function, anything that you wanted to do by visualization and talking about conceptual ideas from the wave function, you can still do that because you can get the wave function.
Yeah, but it's the intuition. How do they develop the intuition so they can figure out how to do these derivations on their own? That's what I find really hard. not just understanding it.
So again, I think the most important thing is to develop conceptual ideas of superposition, entanglement, and so forth at the beginning, and that will build better intuition than almost anything else. That's my opinion. I don't have any research to support that that actually works, but that's my intuition as to what would work best. Yeah.